This is Jack Jackson. We're going to be looking today at triangle similarity in Euclidean geometry and working our way toward a proof of the angle-angle similarity theorem. So you may have seen this before. Hopefully you've done this before. We have looked at a situation where we can control an angle here by this slider. Both of these red angles have this measure here. And then this one controls the common angle here, A1. Which currently has that measure. And notice, because of the angle sum theorem in Euclidean geometry, the measures of the three angles, interior angles of a triangle, must always add up to pi radians or 180 degrees. Therefore, the two angles here at U and U2, notice there they are, they must have the same length, same measure. Okay, so if you can get two angles and two triangles to match up as congruent, the third one automatically happens. So the angle-angle condition implies the angle-angle-angle condition in Euclidean geometry. Now, what we found, of course, is that we don't get one congruence class just with knowing the three angles, at least not in Euclidean geometry. And so what we have here is we have an infinitely many congruence classes. But what we notice is we see the lengths as I have them here, and look at the ratio of corresponding lengths. For example, the length of that side divided by the green one here, or the length of the big side here divided by that corresponding side here, or the side here divided by the length of the corresponding side here. If we do those three ratios, which are right here, notice that they all come out to be the same thing. So as I adjust this, I suppose I adjust it to right here, for example, we now see that every length in the larger triangle is exactly twice as long as the corresponding length from the smaller triangle. So we've actually done a scale factor or a dilation here in transforming the smaller triangle into the larger triangle by a factor of 2. Okay, actually centered up at S. Now, so this is an example of what we call similar figures, or similar triangles specifically. And similar triangles will have all of the angles, all the corresponding angles will be congruent from one triangle to the other. So the angle measures are exactly the same. That doesn't change. What changes is the side lengths, and the side lengths or distances are proportional. Now, we want to prove that as a theorem, that if we have two angles the same, two triangles with corresponding pairs, two corresponding pairs of angles congruent, we want to prove that they're similar. And that's what the focus is going to be of a series of tabs here that we're going to talk about in these videos. And it's a rather complicated proof, so we're going to break it up into pieces. And we're going to have a series of about 3 lemmas here that are going to lead us to the proof. Now remember, a lemma is just a proposition or a theorem. It stands on its own, but its main use is to help us prove a bigger result, in this case the angle-angle similarity theorem. So here's our lemma. Given triangle ABCD, which we ABC, excuse me, over here, we'll let D be the midpoint of this side. We'll have a point E that's between here, so that when we do line DE, it's going to be parallel to line BC. Of course, when we say the two line segments are parallel, we mean the lines containing them are parallel. And we're going to conclude that 2 times DE is equal to BC. Line segment AE is congruent to line segment EC, and triangle ADE is congruent to ABC. So let's work through this. So let's start with what we're given. We're given a triangle ABC, and we're going to construct the midpoint, which we're going to call D. Okay. Now, there's a unique parallel to BC through D, according to the Euclidean parallel postulate. Let's construct that parallel, and we've marked it with these little arrows to indicate parallel. And now we've got line segment DE, and there's our parallel line, E being a point on this side here where that parallel meets line AC, and it will be between A and C. Now, we have some properties of parallel lines. So here we have a pair of parallel lines cut by a transversal, and so we know that by the F property, we might call it, the corresponding angles are congruent. So this angle up here at E and this one here at C are congruent. And similarly, we have a transversal over here to our parallel lines here and here. So the angle up here at D and this one at B are congruent. So if I mark those like that, the angle here, that's the angle DEA and BCA are congruent, and the angle ADE and ABC are congruent, and that's what I've said here in the proof. Now what we're going to do is we're going to take point E and make another line a unique parallel to this line. So we're going to make us a little parallelogram here. Okay, and so let's make that line segment, that line, unique line through E parallel to line AB, and we're going to label its intersection with BC as the point F. Now, I've got the parallel sides marked, so this one here and this one here are parallel, this and this are parallel. Now, we proved an earlier theorem about parallelograms, and we know that both pair of opposite sides are congruent. So we know that DE and BF are congruent, and we also know that EF and DB are congruent. Okay? We also have the fact, we're going to use the fact that this and this are parallel, and this is a transversal, to get an angle right here to be congruent to the one here at B. The angle at F is congruent to the one at B. So let's mark all of that we've got so far. So since this was a midpoint, we have this segment from AD is congruent to the one here from D to B. We have the one from E to F is congruent to the one here. So that means that one right here is congruent to the one up here from A to D, because all three of these are congruent. Use your transitivity of congruence there. And then we also know that this angle is congruent to the one here at D. The one at D and the one at B are congruent, but the one at B and the one at F are congruent, so that means the one at D and F are congruent. So now, and then we already had these angles here congruent, so now we have angle, angle, side, and we have, that's enough to show that those two triangles are congruent. Okay, so what triangles do we have congruent? We have triangle EFC is congruent to ADE. So I'll shade in the interiors of the two triangles we're talking about. So those two triangles are congruent. Well, what does that tell us? Well, for one thing, it tells us all the corresponding parts are congruent. So among other things, we get this from AE and EC. Those are congruent. So E has to be the midpoint of that side. And this one down here from F to C is congruent to the one from D to E, which in turn is congruent from B to F. So in fact, that side is also, F is also the midpoint there. Okay? And I believe that's pretty much everything that we needed to prove. So what do we need to prove? We need to prove that if we take this line parallel through the midpoint, okay, that the point E is the midpoint of this side, so it's right in the middle, so it's the distance from A to E. You're going to get twice as much when you go from A to C. And we get a similar triangle here and here because we actually did it all the way. What did? We proved that all the angles are congruent. Well, we proved this one and this one are congruent, and that one, that one. And since these two little triangles are congruent, the angle at A and E are congruent as well. So now we have so we have similar triangles there. This one should be FEC. Okay, and so we get all the angles, corresponding angles congruent. Okay, well, I'm sorry, I wanted that to be A. What we want to show is that that big triangle here is similar to the smaller one here. So let's look again. So angle A is congruent to itself. Angle C and angle E are congruent. Angle B and angle D are congruent. So those, we got all the angles congruent. And then AD, or AB is twice AD. AE times 2 is AC. And we've seen that now, since these are, each one of these is congruent to that one, CB is twice ED. So that ratio of corresponding sides, AC over AE, AB over AD, and BC over DE, that's always 2. So it's exactly twice as big. So taking it through the midpoint, taking a parallel, you basically cut off a little triangle here that's half as big, lengthwise half as big, angle-wise exactly the same as the one down here. Actually, area-wise, it's exactly 4 times as big for the big triangle, and you can actually see the 4 times as big real easily if we just make this line here. And now we actually are going to have 4 triangles here of equal areas. Not necessarily congruent triangles, but with 4 triangles with equal areas there. Okay, so we have proved lemma 1.